Hey everyone. So I decided that for this day of notes and videos, it might be easier for me to explain some stuff rather than you to just check my notes. So like I said in our previous day, what we're working towards or what we're getting towards are musical instruments. That's what we're building up to when we do this waves and sound stuff. We're getting into musical sounds and different kinds of instruments we know produce different kinds of musical sounds, whether that be a trumpet or a violin. We can play the same note, but they sound different. And that's kind of what we're getting into today. All right, those notes that you hear are resonating notes. And when something resonates, that's a loud sound that we hear. All right, so take a look at my notes here. And for this first little part, there's not going to be a lot of writing on this video. So for this first part, you can kind of look at my notes and listen to what I'm saying. So up there I've got the definition of a natural frequency. And I'm saying that this is the frequency that objects easily vibrate at. Everything has a natural frequency, but what we're usually interested in is some medium like a guitar string vibrating or the air inside of a flute or a clarinet vibrating. And what we can do is we can cause something to vibrate by disturbing it, which is called a forced vibration. All right. Many of you have probably experienced this before, where you take a pop bottle or a straw, and if you blow just right into it, you can get a large amplitude sound. All right. So what I'd like you to do is go over to my notes explanation and take a look at video 1, resonance in glass bottles. So pause this video and go ahead and watch that video. So hopefully you noticed that although those bottles may have looked similar, some were slightly different size but looked similar, they all had some different notes. And they were able to do that by taking a bottle and putting a different amount of water in that. So whether it was kind of empty or really full, you got a different sound or a different amplitude of, or a different note of resonance. All right. So pause this again, and then this time I'd like you to pause the video and watch the resonance in wine glasses. So again, same thing there. In that video, they've got wine glasses all different sizes and then filled with different amounts of water, and that's allowed them to get different notes. All right. Again, those notes that you're hearing are called resonating notes. All right. So if you go back to my notes, I've got the definition of resonance there. And resonance is a large amplitude vibration where the force frequency matches the natural frequency. If we can get our force vibrations just right to match the natural frequency of an object, we're going to get a loud amplitude sound. All right. The best analogy I can use that should help you understand this is thinking about swinging on a swing. All right. So take a look at the video of me talking now. So if you're riding a swing, and let's say these are your legs here. If you're riding on a swing and you sit on a swing, and then you start swinging your legs like this, you probably understand nothing's going to happen, right? In order for you to get a large swing, which would be like resonance, you need to swing your legs in a rhythmic pattern, right? And you have to swing them just right to get a large amplitude swing. And if you've got that large amplitude swing going, and then you start doing this again, then you're just going to go back to the bottom of that swing. Okay? So although we're forcing vibrations in the swing like this by moving our legs really fast, that force vibration is not matching the natural frequency of that rope, or in this case chain. So that means you don't get resonance. Resonance would be a large amplitude swing. Okay? So I'd like you to go back to my notes explanation sheet, and I want you to pause this video, and I'd like you to watch video 3. So again, video 3 there, resonance apparatus, showed you that, hey, if I force a vibration in this object and it matches the natural frequency of either the red, yellow, or the green peg, that one peg is going to resonate, and we're going to get a large amplitude swing from that one peg, and the other ones are going to just have a little tiny vibration. So the other ones aren't going to resonate, and that one is. Okay, This time I'd like you to pause and I'd like you to watch the next two videos. Right? Next two videos are resonance with sound and something that's called sympathetic vibrations, and that vibrations of air molecules can actually cause other things to resonate and have a large amplitude vibration as well. So I'd like you to watch videos 4 and 5, both having to do with tuning forks. The first video is hearing resonance and the second video is visualizing resonance. So pause this video and watch videos 4 and 5. So again, I think that does a good way of showing that if we have a tuning fork and it starts vibrating, its vibration can cause molecules in between to vibrate, and if those vibrate at just the right frequency to hit another tuning fork, then this one can start to resonate as well and make a loud sound as well. Okay? Now there are some applications of this. So for example, there's a product you can buy that's about $10, something called a Vibit. And a Vibit is a little device that you plug into your phone with some music, and there's one little tiny pad on it that vibrates. And this thing that vibrates can cause other things to resonate. And if those other things resonate, you get a much louder sound. So pause this video and go watch video 6 in my notes explanation, the Vibit video. And then last but not least, you've seen this in the Hewitt video already, but I want to talk about it again because now we're talking about resonance. The Tacoma Narrows Bridge, that is a bridge where the wind frequency happened to match the natural frequency of concrete and metal. And since that bridge was thin, that vibration from the wind caused this thing to start to twist, and then eventually we get this wave-like pattern in the bridge, and that bridge collapses. So I'd like you to pause this video and take a look at video 7, the Tacoma Narrows video. Alright, and the reason we talk all about this resonance stuff is getting into talking about resonating standing waves in instruments. Today we're going to talk about vibrating strings. So that can be a guitar, a violin, a viola, a stand-up bass, a cello, anything that is a stringed instrument, a sitar. And then the next 2 days, or next day, we're going to talk about opened and closed pipes, where air molecules are vibrating instead of vibrating strings. So again, what we're hearing when we hear a musical note is a resonating, in this case, vibrating string. All right. So I wanted to start by giving you a visual of this. And what I'd like you to do is take a look at, pause this, and take a look at videos 8 and 9. Okay, so videos 8 and 9 there. Pretty crazy stuff to see, but that's actually what is going on with musical instruments when we play a note. All right, and there's lots of things that can play a role in this, and lots of things that can affect what note we hear. All right, so that can be things like how tight the string is tightened. That can be things like the temperature. That can be like things like how heavy the medium is, how heavy that string is. So what we're going to start talking about today is how we get those different notes by pressing different spots on the fret, for example, for a guitar, or by playing our different strings and how we get our different notes from that. So what I'd like you to do is go back to my actual notes, and you've got a spot there that says definition of harmonics. And I said, hey, these are different frequencies that produce resonating standing waves. All right. The absolute simplest wave pattern we can make in a string, so if I draw my dotted line here for a string, absolute simplest standing wave we can make has a node on each end and an antinode in the middle. All right, and then we can show the other part of that wave as well. So if this were to vibrate back and forth here at our antinode, this is our simplest standing wave. Okay. Now what I say here is that we call this the fundamental frequency. This is the absolute simplest note you could ever play on a guitar string. Okay, and then from there we can get to different harmonics. All right, so for example, a second harmonic is going to have one more node and one more antinode. So it will look like a normal wave. Alright, and then we can show if this vibrated the other way, what our wave pattern might look like. Alright, third harmonic is going to follow a similar pattern. We've now got 4 nodes and 3 antinodes. The reason I'm making this video is because drawing these waves is going to be really, really important for you to solve these problems. So there's my third harmonic. And then, of course, the other part of that wave. Okay? So if you missed me drawing those, jump back in this video and watch me draw those waves again. Now, it turns out that our first harmonic, our second harmonic, and our third harmonic have a relationship between their frequencies. The first harmonic is the fundamental frequency, lowest frequency that makes a note. But the second harmonic has twice the frequency of the first. The third harmonic has 3 times the frequency of the first. All right? So if you hear fundamental frequency and third harmonic, you should know the relationship between those two. Okay? Now, I've got this big table on my note sheets here that's talked about some of the things that that I just mentioned here, like, hey, there's 2 notes here, there's 3 notes here, there's 4 notes here. Okay? But what we're most concerned about are the last 2 columns, the number of waves on string and the wavelength to length relationship. And rather than me just giving you those numbers, I'd like to show you where they came from. Okay? We know that a full wave looks like that. Okay? And if you look, my first harmonic here, that is not a full wave. That would just be like the crest or the top part of our wave. All right? Now, if you've ever seen a guitar, you probably know that the length of the string is fixed. It doesn't change at all, right? So when I say the number of waves that are on this fixed length of string, I can say that this is only half of a wave, all right? Because it's only the crest. And what that means then is that if I wanted to get a full wave, or I wanted to get this yellow part of our wave, or I wanted to get this additional part of our wave, I would need 2 lengths of that string. Here's one length, here's L, but if I wanted to get this yellow part of my wave, or the second part, I would need that again, or a second L. So a wavelength in this case is actually 2 times the length of the string. Alright? So what I want you to do is pause this video, and I want you to try and use the same reasoning for the second and third harmonic, and see if you can justify how I got my answers that I have on my note sheet there. Okay, hopefully you were able to see that our second harmonic has 1 full wave here. Alright, so the number of waves on the string was 1, and that means a wavelength is just equal to the length of the string. But our third harmonic, we have not only 1 wave, so there it is outlined in blue, but we have an additional half of a wave. Alright, or we've got 3/2 waves, or 1.5 waves. Okay? I write this as 3/2 because maybe you've recognized the pattern that the wavelength then to length relationship is just the reciprocal of this number. Right? The reciprocal of 1/2 is 2. The reciprocal of 1, well, is just 1. The reciprocal of 3/2 is 2/3. And we get this pretty familiar pattern of 2/1, 2/2, 2/3. If you had to guess, hopefully you can realize this is going to be 2/4, and so on and so forth. So there's a nice relationship between fundamental frequencies and second and third harmonics, as well as wavelength and length relationships for our string. Okay? So what I'd like to do is go through a couple of example problems. So if you look at the bottom here of my notes explanation, I've got 2 example problems. And we're going to talk through how to do these problems so that you can get an idea of how to approach these problems using these important wavelength and length relationships in my drawings that I've had here. Okay, so why don't you pause the video, grab a calculator, grab something to write with, so that you can try these problems along with me. Okay, so this first one here says a string with a length of 20 centimeters. So first thing I'm going to do is draw a string out, and I know on strings my ends are fixed. Right? Length is 20 centimeters, and I am going to, of course, convert that to meters. All right, that vibrates in the fourth harmonic with a frequency of 3200 hertz. So 3200 hertz. And since this is the fourth harmonic, I'm going to call this F4, just to remind myself, hey, this is the fourth harmonic. All right. Step one is to draw this wave. So why don't you pause this video, and I want you to actually try and draw the wave. If you can draw the wave in these problems, most of the math we're doing is pretty easy. So let's focus on drawing that wave first. So pause the video and give that a shot. Okay, since we are looking at our fourth harmonic, each harmonic up, it's like adding half of a wave. So there's one half of our wave. There's another half of our wave. Here's a third half of our wave. And then a fourth half of our wave. You can see I kind of ran out of room, which is fine. Okay, we still get the idea here that there are 5 nodes. And 1, 2, 3, 4 antinodes. If you want, you can draw the opposite part of the wave. And so that's what our standing wave pattern would look like. The reason we draw this is because now that allows us to come up with the relationship between wavelength and length. So what you're going to do after you draw your picture is look for one full wave. So I look at this picture and I say, okay, there's one full wave. All right? And that's how much of this string or how much of this length. Well, we've got that same pattern again. So that means that one of these waves here is half the length of the string. All right? If you prefer the reciprocal thing, you could say there are 2 waves on this string. So that means the wavelength is half the length. Okay? Now this problem, part B, it says, well, what's the speed of the wave on the string? All right? Thankfully for us, we've got a relationship between the speed of a wave on the string, the frequency of the wave, and the wavelength. V equals F lambda. Except in this problem I don't have lambda, but I kind of do, because I have a relationship between lambda and length, and I know the length of the string. So what I can do is go one line down and say, well, instead of writing lambda, I'm going to write what lambda is equal to. I'm going to write 1/2 times L. And now I can look at this and say, okay, I'm looking for V. Do I know what F is? Yeah, I do. And then I've got my 1/2 here. Do I know what L is? Yeah, I do. So I should be able to solve this problem. All right. 1/2 times 0.2 is 0.1, and 1/10 of 3,200 is 320. Whoops, meters per second. All right. So what I'd like you to do is pause the video, take a look at that second problem, and I want you to try and solve this on your own. Okay. After you unpause this video, my setup will be there, but I won't have actually solved the problem yet. So focus on getting the setup done, and if you feel good, try and actually solve the problem too. Okay, hopefully you have something similar to this. Again, we've drawn our wave here, and I can see that my wavelength here, that takes up 2/3 the length of the string. All right, so again, third harmonic, there's 3 half waves there. That takes up 2/3 the length of the string. So I'm going to approach this problem the same way. And again, I don't know what my wavelength is, but I do know that my wavelength is 2/3 the length of the string. And at this point I have V, and I'm looking for F3. I still got my 2/3, and I know the length of the string. So why don't you pause the video, take a second, and do this calculation. Okay, hopefully you were able to get 825 hertz. All right. So, like I said, I don't think the math part of this part of this problem is too tough. This part of the problem, all this setup in this drawing, this is all very difficult. All right. So practice this part of the problem, and then this comes pretty easy. Okay? So again, we're getting into instruments. We're getting into how do we hear different notes and how do we hear different sounds. We know that different notes or pitches correlate to frequency. So depending on what the frequency is, we're going to hear a different note. This sound would be a much higher pitch than this sound. Okay? Thanks for tuning in. Good luck with the homework.